Charlie there for the Peace Center. And there's my information. I'm Jack Kanack. Everyone knows me here. We're going to talk all about climate change today, and this has been recent in the news here. The doomsday clock has been advanced 2 minutes to 11:57 p.m., partly due to greenhouse gas emissions, which are profoundly transforming the Earth's climate, harming millions of people with sea level rise, diminished food supply, and even more drought, wildfires, and killer storms than we have today. This was produced by the Board of Atomic Scientists. There's a board of 17 Nobel laureates, and that's what they came up with. They advance this clock or take minutes off every year, and part of the reason was due to climate change.
Now, Jack, as far as you know, is this the first time they've included climate change in their calculations?
I do not know, but they mentioned climate change as a big contributor. And another one is nuclear proliferation. The U.S. and Russia are not abiding by their previous treaties and are building up their arsenals. And also there's some regional conflicts due to climate change, like the one in Syria. That conflict was produced by wars. It was a drought, actually. A cold spell killed all the crops by a drought for several years, and they had all this conflict. So as the weather patterns will be changing, people will be locating to where they could have food and shelter, and they're going to go to other countries, and that's where you're going to get your conflict.
You want to pass the sign-in sheet up front here?
What I was going to say too is I go through these slides like Dr. Vermetti. If you have a question, just stop me. Okay, so we can have a discussion as we go along.
Not mine.
Okay. Now, let's go to some costs of extreme weather events, inflation adjusted. This starting in 1960. In the 50s, we had 13 such events. In the 60s, we had 16. In the 70s, we had 29. We had 41 in the 80s, and 72 in the 90s. And in the U.S., from 1980 to 2014, we've had 178 events from severe weather of over $1 billion. And the total cost in that period from 1980 to 2014 was $1 trillion in the U.S. due to extreme weather events. 7 out of the top 10 disasters since 2000 are in this list of extreme weather events with money. For the Northeast, we've had a 74% increase in the amount of heavy rain events, and heavy rain events are 2 inches or more of rain in a 48-hour period. So that's increased here by 74%. And what's been happening is that we've been going from extreme heavy rain events to a drought, to a heavy rain event. So the rain hasn't been spread out like it should be. It's been either a boom or a bust. They say that because of the sea level rise, there's a double the amount of the probability of having a Hurricane Sandy-like event when compared to 1950. And also, what I was going to say, instead of getting one extreme weather event every 10 years, we've been getting one extreme weather event every 2 to 3 years. However, it's kind of been a different event every year. So one year it's been an extreme drought, next year extreme rainfall, maybe one year extreme cold, next year extreme warmth. So we've been having an increased frequency of that happening. All right, let me just flip to the next one. This is a chart showing temperature in degrees Celsius. The middle one, the green line, is parts per million of carbon dioxide concentration. And the last one here is dust concentration. And what seems to happen is every time that you get a trigger, and a lot of times you get dust like a meteorite impact, a volcano that's pyroclastic, it produces a lot of dust in the atmosphere, which temporarily cools us. However, the carbon dioxide lasts in the atmosphere, which warms us up. And it's some sort of trigger that gets, let's look, like, you get the dust going, and then all of a sudden you get carbon dioxide, and notice the relationship between that and temperatures. And what I want to bring out with the carbon dioxide, going back about 450,000 years, this data was a result of the Volsock ice core data. They actually took the ice core data and they looked at it. And what we find out here is that the concentration of carbon dioxide has never been over 300 parts per million in the entire history going back about 450,000 years. Okay, I just want you to remember that number, 300. And also, with the temperature, much of the time in the last 450,000 years, the Earth has been a giant snowball. We've been in an ice age. And only when the carbon dioxide increases do we get an increase in temperature, and we get right over here these little blips, like right now we're in a little uptick. And that's what's been going on. So what I'm also trying to say is that this uptick in carbon dioxide usually takes about 1,000 to 1,500 years to come out, for us to come out of an ice age once we get the carbon dioxide increase. Okay? So what I'm going to do next with this slide is I'm going to see how scientific we are. Notice that our carbon dioxide, our temperatures increase. This is going back the last, well, from AD 0, okay, from Caesar. We had a medieval warm period. The Vikings invaded Greenland because everything was open. Then it started getting cooler. Then the Vikings said, we gotta get out of Greenland because it's getting colder. So what we're having is that little spike here. You know, we're having that little blip. That's what we're having over in here. Now my question is to you, get to about 1600, what would you think that the trend is going to be? Looking at the temperatures here, okay? Notice how it's a sharp dip. And then looking at the trend here, what would you say it was going to be? Anybody? Do you think that the trend is going to go up or down? Just looking at this data scientifically. You would think that we've had our peak and we're going down, right?
Right.
Right? Okay? Well, what happened at about 1750? Anyone remember?
More or less, meaning the industrial age.
Right, the Industrial Revolution. Very good. Notice what happened afterwards. This is the same graph. I kind of truncated it. But notice how it went up. That's how the temperatures have gone up with the Ice Age since the Industrial Revolution. You'd think it would be going down. You'd think it would be going this way. And all of a sudden, it's going this way. We've never had that double dip before. You know, in temperatures. They peak and they go down. So, anyhow, the International Panel on Climate Change predicts that by the year 2100, we're going to have a temperature change, at least 6 degrees Celsius change, And that's going to be only in 100 years instead of 1,000 to 1,500 years.
85 years.
Well, now 85, right,
Yeah.
right, 85 years, which is kind of scary, okay? Let me talk to you now about, for some of you that don't know about the greenhouse effect, what it is. The sun powers all life on Earth. It powers the climate system. Solar radiation is reflected, comes into the Earth's atmosphere. About half of it's absorbed as a surface and it warms it. Now, every star, every planet, they give off, they give off the radiation, but they give it off in wavelengths we can measure called microns. And what happens is that, depending on how hot the body is, the hotter the body, the smaller the wavelength. And the sun, being 9,941 degrees, has a wavelength of 0.483 microns. So it comes through the atmosphere. When it hits the Earth's surface, it stops. And that energy warms up the Earth's surface, because it's like a speeding truck. It comes in, it hits, and it slows down, and it warms, and all that energy warms us up. And when it goes back out into space, when it tries to, since the Earth is 59 degrees Fahrenheit on the average, it's 9.66 microns. And these greenhouse gases that we have are about 10 microns. So they're very close, and what they do is, instead of them hitting the ground and going right back up into space, a lot of them are absorbed by these greenhouse gases and re-emitted in all directions before they get back out into space. So they have a longer residence time. So they're instead of going back and up, down and back up, they're going down, and then they're this way and that way and whichever way, and then finally they get out. And that's what's causing our warming. And the more of these greenhouse gases we put into the atmosphere, the greater, the more warming we're going to get. Now, can you remember how many parts per million I said before? We've never been in over
300.
300, right, in over 450,000 years. We've never been over 300. Well, currently, we're at, notice, before the Industrial Revolution, we were at 280. Now we're closing in on 400. We've never been over 300, but now we're closing in on 400. And it's a 41.2% increase. And if you ever take a course from Dr. Vermet, he talks about increased radiation, watts per meter squared. He has instrumentation on his roof that measures watts per meter squared. Well, what this does is, this is telling you how much extra it adds, 1.88 watts per meter squared of extra energy that we didn't have before. And other greenhouse gas concentrations at 10 microns are methane. We went from 700 parts per billion up to anywhere now like 1900 parts per billion, which is about 170% increase. Because when methane comes from agricultural production, it comes from, they say, oh, this safe fracking. Well, what they do is when they bring up the gas, a lot of it escapes, and it's methane. And that decreases our radiative forcing. We also have nitrous oxide. It's gone up 20%. Tropospheric ozone has gone up 42% since the Industrial Revolution. Now, the greenhouse warming potential relative to carbon dioxide. What this is saying is that carbon dioxide has, over 20 years, has a value of 1, so they're basing everything on carbon dioxide. For 100 years it's 1, for 500 years it's 1. Methane has a lifetime of 12 years, but in the first 20 years it has a 72, this is a conservative number, some say 86, okay? Conservatively, 72 times the global warming potential of carbon dioxide. Nitrous oxide stays in the atmosphere 114 years and has, over the first 20 years, 289 times. And the rest of these are chlorofluorocarbons, and they're in parts per trillion, but some of these, they're in the atmosphere 50,000 years. And they have a global warming potential in the first 20 years of 5,210 times that of carbon dioxide. And and you look at some of these numbers, over 500 years, it's 18,000, 32,000 times the amount of carbon dioxide. So it's a lot of, it's significant what we're putting in. Now, just flip through here. So you have any questions on that so far? The next one, I'm going to tell you where some of this stuff comes from. Carbon dioxide, if you notice, around the blizzard of 77, we were around 335. We're going up to about 400 now, once again. 20% of all the U.S. emissions of carbon dioxide come from agriculture. 17% of global emissions of carbon dioxide come from deforestation, slash and burn, where they clear forest land in the rainforest for agricultural purposes. Nitrous oxide, 44%, notice they're all going up, 44% come from agriculture. 1% of nitrogen fertilizer ends as nitrous oxide. The methane, 36%, comes from agriculture. A lot of it comes from fracking. And the rest of these here are the exotic and parts per trillion, the like man-made stuff. The chlorofluorocarbons, Some of these are going down because they've been banned because they interfere with the ozone layer. So at least something's going the right way. However, what we put in there, some of that stuff is in the atmosphere for, 50,000 years, 10,000 years. So it's still there. It's not going anywhere. Okay, next slide. We're going to take a look at global mean temperature. And this is in degrees Celsius going back from the late 1800s when record keeping started. And what we're looking at is, we got Ken. How you doing, Ken?
Hi, Jack.
We've got a period from, the red line is showing the last 150 years. Notice the slope. It's only saying we're warming about 45 hundredths of a degree centigrade over 150 years. The bluish line is showing us a raise over 100 years of 74 hundredths of a degree centigrade. In the last 50 years, the slope of that line being orange is 128 hundredths of a degree centigrade over the last 50 years. And if you take a look at the last 25 years, we're warming at 177 degrees centigrade. Per decade this is over the last 25 years. So the rate is increasing. And that's a really important thing. Sea ice is going down. In fact, they think that there's going to be no sea ice. It's all going to be melted. Because the current sea ice is becoming thinner, and it's becoming, the oceans are warming up So that water down below is melting from below and from above. And that's going to be a real problem, because once the sea ice goes, instead of having white to reflect the sunlight, we're going to have open ocean to absorb it. And also what it's going to do is it's going to, there's a lot of frozen methane in the tundra, in the Arctic, and what that's going to do is it's all going to release. And what it's going to release is methane. And the methane, being a greenhouse warming gas, is going to be maybe another trigger to get us even warmer that we didn't know before. So that's going down. Yeah. I am just wondering, you got a question here. Let's look at changes in temperature, sea level, and northern hemisphere snow cover. Okay? Going from 1850 to the year to present, the temperatures, mean temperatures, been going up about 1.2 degrees centigrade. The sea level has been going up due to melting ice caps and thermal expansion of water. And the northern hemisphere snow cover, like I showed you before, is going down.
Except in Buffalo.
Well, except in Buffalo, and the reason is because of our jet stream, and Warren gets me going into a good segue here. This is what you hope for every winter. You hope for this. It's a zonal flow. It keeps the warm air over here. So anywhere south of here is, assuming that the flow is right over us. Anywhere south of here, notice how the line goes, just through Lake Ontario, to keep us warm. Anywhere south of here it's warm, anywhere north of here it's cold. And where the difference between where the jet stream is the strongest is where the temperature contrast is the greatest. So what happens is that the air flows from the south to the north, because where you have the warmer air, it's actually under higher pressure. Okay, so it's flowing north. Coriolis effect turns everything to the right in the northern hemisphere. So as it flows, it turns to the right. Okay? But where you have the greatest temperature difference is the faster the flow is, okay? So that's what you're hoping for. You're hoping for a nice zonal flow. But what's happening is, these are different scenarios put out by the Intergovernmental Panel on Climate Change. And they're saying these different scenarios, B1, A1B, and A2, they're scenarios where we're saying, okay, we're going to really try to reduce emissions here and see what happens to temperature. And here we're some countries are going to do it, and here, like we're doing now, no one gives a darn. Okay? And what's happening is that in all these scenarios, if you look at the temperature on the bottom here, the polar areas are warming up greater than the equatorial areas, okay? So there's less of a temperature difference between the pole now and the equator than there was before. And what happens is that when there's less of a temperature difference, your jet stream becomes weaker. And I just want you to think of riding a bike or a motorcycle. When you're on a motorcycle and you're going really fast, you're going straight. When you see a 5-year-old riding a bike for the first time, they're going like this and all over the place, and they're going to fall right and left, and they're wobbling because they're going slower. So the faster you go, the straighter you're going to go, and that's kind of what the jet stream is. And what's happening is that because of the temperature difference, the jet stream is not flowing as as fast as it is, and it wants to, I call it like a slinky pattern, and we'll show you that one. That's what it was last year, and it's the same darn pattern this year. You have a slinky pattern, and this area up in here has a tendency to sharpen, and this wants to even get greater, and this area down here, because there's not much temperature difference, it wants to stay fixed. And that's what's happening. So when you hear the commentators on the radio, you know, some of them, they're not scientifically astute, they will say, well, the scientists say, you know, how can you believe when they say global warming? They say they blame it for us being too hot. They blame us for us being too cold. They blame us for it being too wet. They blame it for us being too dry. What is it? Well, what happens is when you get a pattern like this, like we're in, unfortunately, it doesn't want to move. It stays fixed for weeks or months. And that's what's happening. So the areas like in the Pacific here, like before some of us walked in, Dean was talking about, Alaska was in the 40s today, okay?
High pressure there.
High pressure, 40s, and it's going over Alaska. It's coming down southeast Alaska through the northwest Canada and dumping on us. And we're going to be cold. So these areas are going to be hot and dry. These areas are going to be snowy and cold. And it's all because of climate change.
So the velocity is low over Georgia and North Carolina? So,
Well, yeah,
and it's high over Alaska, the velocity of flow in the jet stream?
that's what they're saying. They're saying that this here wants to the literature I read said this wants to sharpen and actually push further north, but this is kind of lazy down in here and just doesn't want to.
Well, is the velocity the same in both places or not?
Not really, no.
Okay.
I was going to show you a current map of that too.
Now, if you have a sharp difference in air pressure between the highs and the lows, you would think the border of the jet stream would be flowing faster.
Well, the lows, your lows, where you have the difference in temperatures, where you have the air masses. And what I'm saying is that these air masses are sharpening up here. So what I read, which I thought was really interesting, there's three wind flow patterns like in the northern hemisphere. You have the northeast trade winds, you have the southwesterlies, which we're in, and you have the polar northeasterlies. What they're thinking is that the trade winds here are going to increase a little north, and the polar jet stream with the northeast polar winds are going to stop. And it's going to be like two circulation patterns instead of three. And we're going to be in that, eventually, that one circulation pattern with the North Pole. So we're going to have really wicked weather.
So what we're getting now is sort of be what's going to be in the future.
It could be the norm, yeah. But it's going to warm up there, which means it's going to warm up down here, but you're still going to get things like early springs followed by frost.
Okay.
You know, because this pattern might stay like this and then move a little bit. You know, in which you'll be in the colder air.
According to your thing there, it looks like Nevada and all that area, Arizona, is going to have it made.
Well, right now, but the problem is they're too dry.
Okay.
Here's the problem, because I'm going to talk about agriculture later. You have 75% of the aquifer in California is already gone, where they're pumping water for our food supply. They're not getting anything to replenish that. What happens when it's all pumped out? It's going to take 100 to 150 years to fill if they get decent rain every year. So where are we gonna get our food supply from? Because the food supply comes from here in the winter.
Yeah.
Where are we gonna get it from if their aquifers are dry and there's no more water? And that's part of the problem. I don't know if I answered your question.
Could they desalinate the Pacific Ocean, pump it in?
It's very expensive.
Expensive.
But
Desalination is
if you're out
horribly
of
expensive.
aquifer water, what else, what other thing are you gonna do?
They've got to get a new method that's not as expensive.
Well, as long as they don't drain the Great Lakes. I wouldn't want to see that happen.
One of our politicians,
Well, luckily we're with Canada.
Yeah.
Because
That's
if
what
we
they-
weren't with
Canadian-
Canada,
Canadian-
Yeah, Canadian government has already told them that they want to see a shooting war. Go ahead, drain the water.
right,
yeah.
exactly right.
We're lucky we're with Canada. You know, if Canada ever became part of us.
God bless Canada. What can I
Yes.
Thank you,
Absolutely. I was just
Dr.
going to say that, Steve. Thank you for that one.
He said that for you.
I'm actually here just to make sure they don't drain the I'm working for the Canadian government.
Cease is undercover.
That's right, that's right.
All right.
Darn, we blew your, sorry, Steve, we blew your cover.
Jack, we have one more question.
Yeah.
When you showed the previous slide,
Yeah.
where the jet stream goes down,
Yeah.
it will not go more towards the extreme southern states because the trade winds from the Gulf come up and,
Well, it could go down.
It'll still sink.
Let me.
so people in,
I
Carolinas and
brought
Georgia.
this.
I think it'd be great if it went down to Florida, you know.
This is what's happening. This is the current one that I pulled up, valid right now. 00Z on Wednesday.
And you can show Florida there, you can see
See,
Florida.
here's a jet.
Yeah.
look at Florida, yeah,
Here's a jet. See, it's dipping down right where Myrie drives,
yeah, New Orleans.
New Orleans, and it's coming up. So, but you could see it's going way up. It's coming right from northern Alaska, right down on us, and then coming back up. So right here where the jet stream is the strongest is where your temperature difference is. So if you look at North Carolina, part of Virginia, this is where you had your ice storm and your heavy precipitation.
They were supposed to get 8 inches today in DC. I don't know if they did, but
Yeah.
last night's what they were forecasting, because I was talking to my kid sister.
They're right in the bullseye.
But see, this is
Better them than us.
but it's this depth here, and
These East Coast storms then are following the jet stream track north, is that right?
well, that's what they do. They follow the jet stream. I think that's your answer to your question.
Yeah.
The storms follow the jet stream. So, anything that comes by is dipping down and it's riding this right up the coast one after another like an airplane on a runway.
So what's the generator for our weekly East Coast snowstorm? I mean, that's happened for the past month, right?
Well,
So-
it's just this persistent jet stream.
Yeah, but what's
when
the
you're at the
generator?
bottom, storms usually form at the bottom of troughs,
I believe it's
and then they work up the eastern arm, no matter where that
where
is.
they start.
Yeah, so they
And-
start at the bottom
Yeah,
of the trough.
And it
here.
has to do with change in wind speeds
Right.
and the mixing that goes on, and then they kind of form, they always form over Texas, Arkansas, when you get this kind of pattern,
Mhm.
and they'll work their way up through the southeast states and build, and then we can get them running up the east coast when you get that kind of pattern.
Yeah.
If that was moved farther to the west, then Buffalo might be in track
Right.
for some storms.
Right.
Just right now, it just happens to be, we're in the middle of the trough, and we're not getting a whole bunch compared
See,
to
we're on
Boston.
we're on the edge.
Yeah.
So as the jet stream goes north, it oscillates enough so that the western part can get what the eastern part is also getting? In other words, it doesn't go up on a main path. It changes it.
Oh, it changes, yeah. It goes all over the place. But this is the current pattern. Let's look at 10 days out, just to see what it is. That's what it looks like in 10 days.
The same thing.
Generally, not as deep,
It's
but
not
Yeah,
as
it's not
deep,
as-
though.
it's not as deep.
it's still there.
It's still very active in the southeast, though.
I mean, there's no reason why at some point in time we cannot get locked into a ridge situation, and then we're going to be complaining about really warm temperatures and so on. It's just
Hopefully not in July.
these last 2 years, we've been locked into this trough here, and the
Right.
west has been locked in a ridging kind of formation. But again, in another year or so, it theoretically could reverse, and we could be under the ridge and enjoying a nicer winter and a very hot summer
Yeah.
and so on.
See, I-
What is the temperature projection for us in 10 days?
Surface,
It's 1,000 millibar maybe on this one?
yeah, yep.
That's the closest.
So we are in, well, right now, that's what we are, we're in the blues, so we're -60 Celsius, which is, what we are. And
same.
it's showing in 10 days,
We're still there.
we're
Still there.
We're still, well, we're a little bit colder in 10 days.
I don't think anyone's talking about any kind of warmth for a while, so it's a couple weeks at least.
I just want to show you,
February may go through the month without ever reaching
Yeah.
just
It
32.
could be one of our coldest
I-
months.
Yeah.
Definitely.
I just wanted to share this with the people that were here.
Oh, I love this, yeah.
Yeah.
Yeah,
Kind of like Rick Mertz training.
a little break here.
And this is Celsius too.
I can't go out there.
I'm not going.
Let's just call that weird kid.
I called him. The kid says he's had it.
The whole 5-day forecast is freezing.
What about day 6?
Freezing.
What about day 7? Rob, what is it?
+1. +1. Waited so long for something like this.
At Environment Canada, you'll frequently see a +1 somewhere near the end of our 7-day forecast. We put that there to keep you from going to dark places mentally and possibly destroying property.
What are you gonna do when it's +1?
I might get the ice pick and chisel open the back gate.
Maybe you'll buy toothpaste and soap.
Personal hygiene, I forgot about that.
We don't know if it'll really be +1. 7-day forecasting is kind of a sham anyway. Anything past day 5 is just throwing darts. So might as well give you all a reason to hang on.
Well, Thursday's not +1 anymore. It's -15.
What about Friday?
+1.
Suckers.
Get back to the car!
Environment Canada, cloudy with a chance of making stuff up.
This track even has a laugh track on it, doesn't it?
And that was from Rick Mercer.
That's Rick Mercer.
Oh,
He's good.
he's hilarious.
Tuesday night CBC at Tuesday night at 8 o'clock.
Yeah, he's funny.
He's good.
He's
Half-hour show and it's well worth watching.
And if you don't laugh, you better.
One of the interesting things you brought up, Jack, was
Yeah,
the real reason for all this happening
Yeah.
is the difference between the equator and the poles.
Right.
In terms of the temperature getting closer
right,
and having the effect that it's doing.
right, that's what it is. You got it.
Now, the odd thing I saw was usually you expect a negative NAO in this kind of pattern.
Yeah,
And we're nowhere near negative
Right.
NAOs. We've had
Exactly.
persistent positive NAO.
right,
And that's a little bewildering why this pattern has stuck like this when you
Right.
don't have that NAO.
right.
Is it because the jet stream is cut off or something like that?
I don't know. I mean,
It's-
what usually causes this blocking like this is you get the negative NAO and it brings down the colder air. And the positive NAO gives you more of that zonal pattern that Jack showed earlier.
Right.
And we've been into a positive NAO for a long time now,
Right.
and we just can't seem to break that trough. And so that's kind of a little bewildering, because most of the time, we were predicting for Buffalo's weather, you see negative NAO for the winter, and you say cold winter. Now someone's going to look at the data and say positive NAO and cold winter, and it just doesn't make colder, but that's the answer. It just doesn't make sense, so there's something else going on.
Yeah, I know. It's beyond my
Yeah.
pay grade.
Yeah.
That's honest.
So I think a lot of people are kind of scratching their heads about that. I love this slide.
Well, this is from January 2014.
14, okay, yeah.
But what I wanted to show you here is, see, people think that since you live here, it's cold. And everyone's cold, but the red is warm. A lot of people are warm. That's what I'm trying to show on that slide.
They used to be cold.